All right, this lecture will cover Newton's second law and momentum in special relativity. Now, what was Newton's second law from introductory physics? Well, we found that a force applied to an object of mass m yields an acceleration a. Both the acceleration and the force are vector quantities. And we also learned then that this can also be expressed that the force induces a change in the momentum of the object. It's related by the derivative d dt of the momentum p, where the linear momentum p, it's a vector, is just the particle's mass times its velocity. And velocity itself is just the time derivative of its spatial position x, which again is a vector. Now, here I've used the letter u to denote the velocity of the object. And you may be more familiar with v, and in fact your textbook may be using v. But I'm using u here so as to distinguish it from the velocity v used to convey one inertial frame moving relative to another one. You could do it the other way around, but we just don't want to mix up the velocity of the object in a reference frame, which I'm calling u, to the velocity of one reference frame to another, which I call v. All right, but back to our message. Momentum is mass times velocity in introductory physics. And Newton's second law is that the force is the rate of change of the momentum, or mass times acceleration. But let's see what is a problem here for special relativity. We learned if we do transform from one reference frame to another, we have to apply a Lorentz transformation on the coordinates. But x and t transform differently from one reference frame to the next. In fact, they get mixed up, right? X will be a combination of x prime plus t prime times a factor gamma, and t will be a function of t prime and x prime also, but with a different kind of equation. And so it's going to make a mess when we do a transformation. It's not going to look like a simple equation, f is dp dt. The form, the so-called form of the equation for Newton's second law would change from one frame to another, and therefore meaning that it would not look the same. But the laws of physics should look the same from one inertial frame to another. We don't want to have to write another set of Newton's laws for one reference frame versus another, because there's an infinite set of reference frames. So we need the laws of physics to look the same for it to be an inertial frame where the laws of physics hold. And this is kind of a subtle aspect of relativity. We need the laws of physics to look the same in all inertial frames, just like Maxwell's equations need to look the same. So let's start over. Let's try to redefine momentum. And then from there, we'll have a modified form of Newton's second law. So this introduces the concept of relativistic momentum. So let's define momentum this way. It looks similar. Momentum is going to be the mass times a derivative of its position x, but the derivative is with respect to something called tau, where tau is the proper time in the object's reference frame. So it's dd tau. This is also known as t naught for tau. They're the same thing. It's just the time that's elapsed in the reference frame of the object. But for a derivative, it's just more compact to write tau rather than t naught. Okay. You might say, well, how does that get around it? Well, everyone can agree on what is the reference frame of an object. If we're not in the reference frame, we know exactly the Lorentz transformation to make from our frame to the reference frame of that object. There's no ambiguity. The reference frame is when the object is at rest in that frame. So everyone knows what that frame is. Everyone can compute this derivative in that frame. So the denominator of the derivative is the same in all reference frames, the d tau part. We can rewrite this for another frame that is not the object's reference frame because the numerator does change. So let's expand this out a bit. Let's write that the momentum p is m dx d tau, but we can write this as m dx dt, the time in that reference frame, provided I multiply by dt over d tau. So essentially the dt is canceled, but it's a Jacobian transformation there essentially. Now, from time dilation, we know that time is not the same in different reference frames. It differs by factor gamma. So if I'm in the rest frame and I want to go to a frame that's not the rest frame, I have to multiply gamma by gamma the time in that rest frame. So from this relationship, dt d tau, the derivative of gamma tau with respect to tau, is just gamma. So this dd tau is just the factor gamma. And the other derivative, dx dt, well, that's just the normal definition of velocity, which I'm calling u. Dx dt is just velocity. And so the new definition for momentum is tantamount to just saying that momentum p is going to be gamma mass times velocity, where gamma is 1 over the square root 1 minus u squared over c squared. So the difference from the non-relativistic form is that we have introduced this factor gamma out front. Right, so that is our new definition for momentum, the relativistic definition that we will use in this course. And note that u is the velocity of the object in the reference frame, and it's also the velocity used in this factor gamma, which should not be mixed up with the gamma that goes from one reference frame to another. That velocity might be v. Excuse me. Okay, armed with that definition for momentum in relativity, let's go back to the concept of force. With the previous definition for momentum, we can retain the definition of force as per Newton's second law. So in other words, Newton's second law is F is dp dt, the change in momentum with respect to time. But we have to put our new definition of momentum in there, so it's d dt of gamma mu, where this gamma is with respect to the velocity of the object in that frame. So I put a little subscript u there. Now, the component of the force perpendicular to the direction of a Lorentz boost can be given by this. We can talk about the perpendicular force to the direction of the boost. So if the boost is along the x-axis, we're talking about the force, say, along the y or z axes. So in that case, force is just dp dt, and momentum is just gamma u mu. So I can pull the mass out, and I have, well, from the earlier definition of mass times dx d tau, I have mass ddt of dx d tau, which I swap the order of the dt and the d tau as m dd tau of just dx dt, which is the transverse component of the velocity for the transverse force. Then if I convert from, to take these derivatives, the dd tau of this and the ddt of the velocity, I get a factor gamma from here. So I have m gamma, and then the time derivative of velocity is just acceleration. So put it another way around, and maybe this is somewhat trivial to have worked out, is that the transverse force is just gamma m a transverse. So the acceleration in a transverse direction times mass times gamma for the particle in that frame, that is the transverse force. So it's not F equals ma, it's F equals gamma ma in the transverse direction. Now, if we want to consider how this force transforms under a Lorentz transformation, then the formula does get a bit more complicated as we transform. But we could do that if we wanted to. A component of the velocity transfers to a boost along x transforms as the following. So we learned this when we learned about the addition of velocities from one frame to the next. But now we're talking about the transverse velocities, not the velocities parallel to the boost direction. And anyway, from those lectures, the transverse velocity in one frame is that of the transverse velocity in the prime frame divided by gamma and divided by 1 plus v ux prime over c squared. Okay, now there's a couple things going on here. There's a gamma v, this is the gamma factor from going from one frame to the next. So the speed of one frame to the other relative to the other is v. So this gamma depends on v. Whereas the earlier gamma for the definition of momentum and force was with respect to u, the velocity of a particle in that frame. So anyway, this is how the velocities transform. So force transforms, recall, as from the earlier equation, it was m dd tau ddt of u perpendicular, where u perpendicular is transformed this way. So we need to take this derivative of dd tau of my perpendicular velocity. Here's the perpendicular velocity. And so I put in the expression for how the velocity transforms, take that derivative with respect to tau, and I'll find that essentially I have a definition for the transverse force in the primed frame, and then divided by gamma v, 1 plus v ux prime over c squared. So it looks very much like the transformation of velocities, but now I've replaced it with force for the transformation of forces, at least for the component perpendicular to the direction of motion of the two frames. All right, important takeaway here was the relativistic definition of momentum, and also that we can compute force to use in Newton's second law in relativity.